Well, welcome again to the Picture Language Seminar. We've been spending a lot of time at home, so I think we can continue our seminar throughout the summer, which is very unusual, but until something else happens, I think it's a good idea. And for the next 3 weeks, we have interesting speakers, Marius Young next week, Paul Fendley after that, and Vaughn Jones in 3 weeks. So today, we're really pleased to have Robert Raussendorf. He's at the University of British Columbia. He's an expert and one of the moving people in measurement-based quantum computing and in contextuality. And today, he's going to tell us about a hidden variable model for universal quantum computation with magic states on qubits. So I'll stop sharing my screen and let you do it. Robert.
Yes, I try. Let's see. Oh dear, what was my calendar open? Okay, where is all that stuff open? Okay, can you see my screen?
Everything's working.
Yeah. Okay, fantastic. I think then we can get started. So indeed, the title of my talk is a hidden variable model for universal quantum computation with magic states qubits. I'm very happy to be here in your seminar and able to talk. I mean, a year ago, I would not have imagined talking about a subject like this. So there's surprises every year in science, and that's certainly a good thing. I would also like to point out, I mean, we've just seen all these symmetric objects on Arthur's coffee table in his office, and this talk will have to do a lot with symmetry. So let's get started. I would like to point out that this is joint work with my student, Michael Zurel, and my postdoc, Cihan. Okay, and there's a preprint number if you want to read up on a couple of details. Okay, oops, let's see. Yeah, so I'm not really a quantum foundations person. I am a quantum computing person. People like me ask questions like, what makes quantum computation work? And that surprisingly got us in this foundational area. So as soon as you ask this question, what makes quantum computing work, you get lots of suggestions thrown at you. So there's the largeness of Hilbert space, there's superposition and interference, entanglement, of course, recently also contextuality and Wigner function negativity. With negativity in Wigner functions, we have dealt quite extensively in the last couple of years, but we are now transitioning away from it. So we have discussed other structures that we don't know a proper name for yet, but what we know is that these structures are algebraic. And basically we are going from here, from the Wigner functions to those structures. I hope you can see my mouse pointer. I'm going back and forth. Good,
yes,
very
we
good.
do.
Thank you for your feedback. So this brings me to another point. I encourage questions. So please, let me get to slide 4, but also please ask questions so that I kind of can adjust my my speed and my talk. Please ask questions throughout. Okay, so what's the result?
Maybe, Robert, you should stop at a certain point and just, if people don't ask questions, ask them 4 questions.
Yes, I will go through the list. I see all your faces here. I will choose people. No, I will not. Okay, but anyway, please ask questions and I will make stops when suitable. Okay, so now what are we talking about here today? So this is the first paragraph of our recent preprint. And I want to read it to you because this is kind of new terrain for us. And it's kind of, I had not imagined a year ago that I would write a paragraph like this. But anyway, let me read it to you. It is often pointed out that the fundamental objects in quantum mechanics are amplitudes, not probabilities. This fact notwithstanding, here we construct a description of universal quantum computation. and hence of all quantum mechanics in finite dimensional Hilbert spaces in terms of Bayesian update of a probability distribution. In this formulation, quantum algorithms look structurally akin to classical diffusion problems. All right. I think most of you, I would imagine, think of this as something counterintuitive. So, okay, let's get started with this. So here is a more technical summary of the result. So we are constructing a hidden variable model that represents everything that we need positively, that is by probability distributions. So what is represented? All quantum states are positively represented, and also a bunch of operations are positively represented, namely the so-called Clifford unitary gates. If you don't know what a Clifford gate is, I will define it later. And the Pauli measurements. So you see, while the states are unrestricted, the operations are restricted. Unitary gates that are positively represented are restricted, and measurements that are positively represented are restricted. However, these restrictions are relatively benign. Namely, if you have those computational primitives, that suffices for universal quantum computation. So we can represent universal quantum computation by a sequence of probabilistic updates. So this is what I want to talk about. I pause for questions.
Hi, Rob. May I have a question?
Sure.
How many bits do you need to represent a quantum state?
How many bits? Yeah, so that not, I mean, we haven't worked out the details. We only know a lower bound. The lower bound is quadratic in the number of qubits, but we expect this bound to be very, very loose. So very, very loose. So we expect the memory requirements to be large. I can't be more specific at this moment, but what I can say, and that is important, that the number is finite. So,
exponential or just polynomial?
It is probably going to, well. So let me talk about this graph here a little bit. Yeah, let me. So this is the one qubit situation. So the cube that you see here is the state of positively represented states in our model. And well, I guess you would be, if I tell you that this is about one qubit, then you would be looking for the Bloch sphere. The Bloch sphere is not shown in this picture. The Bloch sphere would be inscribed in this cube such that it touches the cube at a bunch of points here on all those faces. Okay, so this is the object that we are dealing with. If we have one qubit, our state space is a cube. And so what we need to update under the dynamics are these face point operators, or these corners of the cube. So whenever you do a measurement, so what's shown here is a Pauli measurement sigma z, and you're updating these face points probabilistically. So say you were here to begin with, then there's a 50% chance that you move over here to the other side, or that you stay in place. Okay, so the reason I'm telling you all of this.
Can I ask a question? Does this mean that
yes,
the cube represents a physical qubit, but there are many logical qubits?
Yeah, so in this case, there is no difference between logical and physical qubits. So we, I defined the model of computation later. So there's no error correction here or anything. But I'll get to that later. So I'm still in the process of answering the earlier question, so about the scaling. So the reason I have been telling you all this is that the object to be updated and the object to be kept in memory are the coordinates of those corners in our state polytope. And so for 1 qubit, you obviously, as is shown here, you have 8 such extremal points. If you're going to 2 qubits, you have something like 22,000. So that's what I can tell you. So the number of these extremal points grows extremely rapidly with n, with the number of qubits. And so that hints at an unfavorable, possibly exponential scaling. But this is not the last word on the subject. I just want to point this out. There would be more to say, but I want to leave it at that. Let me leave it at that for now. Okay, so that's this.
Yeah, quick question. What are the 2 states of the qubits in this representation?
I mean, well, a qubit is still a qubit. So I mean, you can choose any basis you like. Presumably, you would choose the eigenstates of sigma z, plus or minus 1 eigenstates of sigma z. That would be a perfectly valid choice. Yeah, and okay, so basically the sigma z eigenstate in this picture would be at the center of the top face, and the sigma z eigenstate with eigenvalue -1 would be at the center of the bottom face in this picture. Okay, so my qubits are just conventional qubits. But I will define the computational model in a moment, and then hopefully it will be more clear what the computational model is that I'm talking about. I just wanted to say, this is a summary of the result, and I want to talk about this, what you see here, in detail.
So can I ask a question?
Sure.
Yeah, so what is actually determines this connectivity between the, like, this red arrows that you have, why they are not all connected? That's not sort of like, or which one should be connected to which, or you just showing some of them?
No, so this represents a concrete thing. This represents the update on the Pauli measurement. And for this case, I have shown all the connections. Yeah, so every arrow represents a hopping with 50% probability. So say if you are on this vertex and the operation is a Pauli measurement of sigma z, you either stay where you are or go across a face, and both happen with 50% probability. So for the 1 qubit case and this particular measurement, everything is shown here. But this is just an example, and you can imagine if you already go to 2 qubits, you have 22,000 of these vertices, so everything gets pretty bewildering. But the point is, if for all n, it's a finite number of vertices. It's a finite number.
Okay, yeah, thanks.
Good. Okay, so then let's move on a little bit. Let me tell you something about the history of the subject, at least our direction, where we have come from. And this has to do with Wigner functions, and I'll tell you in a bit where Wigner functions come in. But I mean, Wigner functions are obviously an object first talked about in the field of quantum optics. And if you have a Wigner function, then, well, that's a function on a quantum state, or defined for any quantum state. And if that Wigner function dips below 0, that is taken as a sign of quantumness in quantum optics. And we quantum information people have adopted this point of view and made it rigorous for our computational settings. Okay. And well, after this theorem, and in fact 3 theorems applying to slightly different settings. So applying to 3 different settings. So the theorem says the following. So this is the connection between quantum speedup and Wigner functions. Quantum computation with magic states can have a quantum speedup only if the Wigner function of the initial magic state is negative. Okay, so there's a bunch of terms here in this theorem that we have not yet defined, like quantum computation with magic states, Wigner function, initial magic state. So, and we are going to find all these, but since we don't have them yet, let me give you a simplified version of this theorem. And so this simplified version says, negativity in the Wigner function is necessary for quantum computation. And this result has been, for speed up in quantum computation, this result has been applied in different settings. And so what matters here is the local dimension of your Hilbert space. You have qubits, a certain number of levels. And if this dimension is odd, then things are much easier than when the dimension is even. So you see, this is the odd dimensional case, 2012, qubit case, 2020, 8 years in between. So there must have been an obstacle, apparently. Yeah, so this is a result that I want to spend a significant amount of time with in my talk today, just for motivational purposes. But the result that I want to talk about is a different one. So, I mean, technically, we are not objecting to the correctness of this result up here, but if you think about it in the simplified version, so then it sounds almost as if negativity was some kind of substance, some kind of resource. And we want to object to that point of view. So what we say is, this result hinges on very precise definitions that you make for your Wigner function and so on and so forth. And if you choose these definitions slightly differently, then negativity completely disappears from the picture. Negativity is then no longer necessary to describe universal quantum computation. And that counterpoint is what the purpose of my talk is. This is what I want to tell you really about. But I will spend a significant amount of time with this up here. Let me pause again for questions. Okay, there's none right now. So I hope I'm not losing you here, but anyway, I will explain all these notations that are on that slide. So here's an outline for my talk. So my talk has two parts. The first part is basically a review of a particular scheme of quantum computation, namely quantum computation with magic states, and of Wigner functions in finite dimensional state spaces. So we want to go through this computational model and then explain why Wigner functions come in here at all. And then I want to also tell you about why the case of qubits is so much more complicated than the case of odd dimensional local systems. But that has a resolution. Anyway, this is kind of my background material, and the second part of the talk is the real talk. So then I'm talking about the result, the hidden variable model that I showed to you basically on my second slide. And yeah, then there's I think it looks kind of weird. And so we have to do a bunch of consistency checks. We check compatibility with the PBR theorem. We check compatibility with Gleason's theorem. And then we come back to the subject of Wigner functions. So this is the outline of my talk. This is what I want to tell you about today. Okay, so let's define our setting. So this is about a particular model of quantum computation, so-called quantum computation with magic states. So, I guess you are familiar to some degree with the circuit model of quantum computation. And this model is very closely related to the circuit model. There's just one tiny little twist. So, in this model of quantum computation, you have gates, and you see them here. You have the C0 gate, and you have a Hadamard, and you have a bunch of other gates, and you have measurements. But these operations are restricted. You do not have every unitary gate. You don't have a universal set of gates available. And also, you do not have every measurement available. So here is the restrictions. The unitary gates are confined to the so-called Clifford gates. And Clifford gates are defined by the property that if you conjugate a Pauli operator, any Pauli operator, by a Clifford gate, you get a Pauli operator back. So that would not every unitary gate would do that, but that's a defining property of Clifford gates. You take any Pauli operator, conjugate it under a Clifford gate, get a Pauli operator back. So what you see here are examples. The C0 gate is of that type, a Hadamard gate is of that type. Of course, the identities of that type. That is your restricted set of unitaries. Also, your measurements are restricted. You can't measure any observable. You can only measure Pauli observables. Local or non-local doesn't make a difference, but they have to be Pauli observables. Tensor products of sigma z's, sigma x's, and sigma y's. So that's what you can measure. And that's a restriction. And so this set of operations is not universal. And furthermore, if you have only these operations, you can classically efficiently simulate this type of computation. That's the content of the Goddess-Menil theorem. So those operations here, this restricted set of operations is kind of limited, very limited in fact. And so there's a way of making up for it. So you have thrown gates out. It's not a universal set, but you get the computational power back by including those magic states. So the magic states, they are not particularly entangled, just one qubit states in the limiting case, but they are not eigenstates of Pauli operators. They are not stabilizer states. And if you choose these states cleverly, you get universality back. The capacity to do all quantum computations you want to do. So this is a universal model of quantum computation. And so this might look odd. Why this complication with the magic states and so on and so forth? So this computational model is not an oddball. So it is, as of now, the leading scheme of fault-tolerant quantum computation. If you care about decoherence and that sort of stuff, you would implement fault-tolerant quantum computation in this fashion. Gives you the largest threshold and the best overhead scaling. So this is not, I'm just telling you that this is actually quite a popular model of quantum computation. But we are not interested in practicalities. We are interested more in the theoretical foundations. And what you observe here is that with this restricted gate set, you're shifting computational power from the gates to the states. And when you do that, you can now ask the question, which properties must the magic states have to enable speed up? And an answer to that question has been given. And that answer is that the Wigner functions of these states need to be negative. So I'm now transitioning to the subject of Wigner functions. And before that, let me pause again for questions. Oops.
Yes, so I actually have one. I'm a little confused about what kind of measurements you're allowed to make, because if you take the Pauli matrices, that gives, plus the identity operator, that gives you a basis. So I guess I don't understand. Aren't you getting all measurements if you include all the Pauli operators? Or maybe I don't know the definition of your Pauli operator.
No, I think we agree on the definition of a Pauli operator. So, but all I'm saying is that a measurement that you have not at your disposal, for example, is the measurement of the observable sigma x plus sigma y.
Oh, you don't allow linear combinations?
Yeah, we don't allow linear combinations, only Pauli operators.
I see, thank you.
Mm-hmm. Thank you. And other questions? Okay, if there's no other questions, let me race on. Oh dear, I need to cut stuff out. I'm already well advanced in time, not in slides. Okay, so here again is the result that I want to talk about for the first part of my talk. Quantum computation with magic states can have a speed up only if the Wigner function on the initial magic state is negative. So again, this is the result we want to talk about. Now, so this brings in the Wigner functions. And the next goal here in my background section is to explain to you why it is that Wigner functions come into this subject at all. Okay, so let's talk about that, and let's back up a little. So let's go back from quantum physics to classical physics, say classical statistical mechanics on phase space, Liouville's theorem, and that sort of stuff. So in classical statistical mechanics, you would describe physical systems as probability distributions over position and momentum. If your classical statistical mechanics system was in fact a classical mechanics system, then your probability distribution for that system would be a delta peak. Yeah? It would be peaked at some momentum in some position. Now, moving over to quantum mechanics, you can't have that. The Heisenberg uncertainty relation forbids it. And so you can ask, what is the closest thing to this probability distribution that's compatible with quantum mechanics? And such a thing exists, and that thing is called the Wigner function. Okay, and there is an expression here for Wigner functions that quantum optics people might be familiar to. If you're not familiar to this beast, doesn't matter for the purpose of this talk. I'm just saying a Wigner function is a rigorously defined thing. And for the purpose of this talk, we need to adapt it to finite dimensional state spaces. Okay, but again, the kind of the property that quantum optics people have identified as a genuine signature of quantumness is negativity in Wigner function. So whenever the Wigner function of your quantum state dips below 0, then quantum optics people think that something genuinely quantum is going on. And quantum information people have adapted this point of view to their setting. So Wigner functions can be adapted to finite dimensional state spaces. What is that state space? So if, I should say, with a restriction of the dimension of the local system being odd. So there's a lot of difference between even and odd, and I come to that. But if the dimension of our local system is odd d, and we have n of those systems, then the phase space, the corresponding phase space is a d to the n by d to the n grid. So here you see an example for a single qubit. D equals 3 and n equals 1. So your phase space is a 3 by 3 grid. And that is what you see here. 3 eigenvalues for position, 3 eigenvalues for momentum, spans the phase space. Okay, so I hear a sound. Is there a question?
I think I do. So,
yeah.
So I think like when you're now describing this Wigner function and like, you know, like attributing this quantumness to this negative value of the Wigner function. So I'm sort of still like not very clear on that. So,
okay.
I mean, like, because like the quantumness already should be included in this like commutation relation that from the beginning I'm defining this Wigner distribution, right? Then why it should be negativity? Like I'm trying to understand it in a more intuitive way.
Okay, good. I mean, I don't know what intuition quantum optics people have. I'm not one of them, but we will come to answer your question for the setting of quantum computation. So, and this is coming up on the next couple of slides. So, as you will see, if the Wigner function has no negativity, if the Wigner function is positive, then you can design an efficient classical simulation of your quantum computation that is based on sampling. So if there's no negativity, then this is just a probability distribution, and then you can, as we will see, design an efficient classical algorithm that just samples the evolution. And yeah, so your speedup is gone if there's no negativity. So, okay, but that's a preview, and we'll see this in considerable detail. So let's get into that.
Okay.
Yeah, the quick question. The phase space, you're going to choose any pair of Pauli operators?
In
the qubit or qubit context, what are X and P's?
Okay, what are X and P's? Okay, sorry, I do not have a slide for that, but these are just the generalized Pauli operators. So for the sigma z's, it is diagonal matrices with entries that are the dth root of unity. Huh?
Yeah,
and your Pauli X is basically just a shift operator that kind of lifts every level one higher up, and the highest level goes back to the lowest level. These are fairly conventional definitions. Maybe you call them Heisenberg-Weil operators or something.
Can I ask a question?
Sure.
Can you prove that for all completely incoherent operators, this Wigner function would be positive, which is the inverse of what you mean negative for quantumness, sign of quantumness.
Yeah.
Therefore,
Good.
inversely, you should demonstrate that it is positive otherwise.
Yes. I mean, positivity of such a Wigner function is a special situation, and that there is a theorem about those things in quantum optics. It's called Hudson's theorem. So in the infinite dimensional setting, if you're dealing with pure states, the only states with the positive Wigner functions are the Gaussian states. And so that's called Hudson's theorem, and it has a counterpart here in our quantum information setting. So the only positive, as long as the Hilbert space dimensions are, the only positively represented pure states are the so-called stabilizer states. So the stabilizer states are the eigenstates of Pauli operators. So all of them are positively represented, and they are the only positively represented states.
Okay, thank you.
Good. All right, then. Let's go on. So I'm not giving you the definition of the Wigner function. You find it in David Gross's PhD thesis. What I am talking about is properties of these Wigner functions on finite dimensional Hilbert spaces. So the important properties that we need to understand the result that I showed you. The first is covariance. So it turns out that the Wigner function of interest transforms covariantly under all Clifford unitaries. So remember, Clifford unitaries were the unitary operations that I had in this computational scheme. And one of the reasons that Wigner functions come in is that the Wigner function transforms covariantly under these operations. So let's take apart this formula about covariance. So there's two states that we are talking about, the general state rho, and then a transformed state, the same rho, but conjugated under some Clifford unitary U. Okay, and so we want to compare those two Wigner functions, the Wigner function of the old state rho and the Wigner function of the transformed state. And it turns out, as long as U is a Clifford unitary, there's a very simple relation between the two. Namely, if I want to figure out what my new Wigner function is at a particular point in phase space, then this is equal to the Wigner function of the old state, of the untransformed state, at some other point in phase space. And that's kind of simple. So the same in pictures looks like this. So here is my untransformed state rho. So for now, I'm taking a delta peaked Wigner function, not a physical state, but once I know its behavior, I get everything else by linear combinations. At any rate, so this is the Wigner function, delta peak somewhere located in phase space. I apply a Clifford unitary to it, and all that happens is that my peak is shifted to some other location in phase space, and the shape of that peak remains intact. Okay, so this is the update of Wigner functions under Clifford unitaries, and that's something important for our simulation algorithm. Next thing, there's another evolution that matters, and this is the evolution under Pauli measurement. So it turns out if I have a Pauli measurement, then positivity of the Wigner function is preserved. So here's again the formula for this. So this projector P is a projector under a Pauli measurement. So A is the label for the Pauli observable, S is the outcome. Okay, so we have the untransformed state, and we have the state after measurement. And so if the original Wigner function is positive, then so is the Wigner function after measurement. So positivity is preserved for all Pauli measurements and all outcomes. Okay, again, there's a pictorial representation of it. And in fact, the picture shows a little bit more than what the results showed. So here is the Wigner function before the measurement. Delta peak located at some point in phase space. When you do a Pauli measurement, the Wigner function smears out. It's no longer peaked, but it has now support on a ridge. That is, it has now support on a line in phase space. And in fact, the Wigner function itself is just the probabilistic combination of all these delta peaks here. So the Wigner function spreads out on the line, but it remains positive. And so these two properties of the evolution of Wigner functions are now important for our result. And here is the proof sketch. So, dear, I'm not doing well with time at all, so I need to speed up a little. But let's just finish this thought. So this is just as a reminder, this is what I wanted to show you. So if the Wigner function is positive, then we have an efficient classical simulation, and hence there's no speedup. So we want to show that there's an efficient classical simulation. So we're using the properties that we've just established. So if our Wigner function is positive, well, then it's a probability distribution that can be sampled from. So each sample would be a point in phase space. And now in our algorithm, all it consists of is Clifford unitaries and Pauli measurements. And we know how to update points in phase space on these operations. So for Clifford unitaries, it's a deterministic update. For Pauli measurements, it's a probabilistic update, but it remains a simple update. So we can indeed, as soon as our Wigner function is positive, we can indeed efficiently classically simulate by sampling, and hence there's no speedup. Good. All right, so this ends a portion of this talk. So I wanted to illustrate to you why negativity in the Wigner functions is needed. And this is kind of what the point that all these older paper makes. And now I want to begin the transition to the subject of our talk, my talk proper. But I want to be quick here about the trouble with qubits. So for qubits, the whole thing is a lot more complicated. So what we've so far done is taking the original quantum optics Wigner function in infinite dimensional state space and adapted it to finite odd dimensional state space. And that was fairly smooth. But if you go from finite odd to finite even, then all hell breaks loose. So the even case is considerably more complicated than the odd dimensional case. And the reason for that is these little monsters here. So they are called Mermin square and Mermin star. And I hope some of you know them. Can I just get a hand here? How many people know what Mermin square and Mermin star are? So this is a subject I can't get into today. So that has to do with the quotient-Specker theorem. The fact that quantum mechanics is contextual. And these little gadgets here give you very simple proofs of the quotient-Specker theorem. And they exist in even Hilbert space dimension, but not in odd Hilbert space dimension. And this subject of contextuality is very intimately related to all our Wigner function stuff here. And because you have those guys in even dimension, you have a lot of trouble in even dimension. So let me talk about this just a little bit. So here's our Wigner function. So this is now a definition of the Wigner function that works both for the even and odd dimensional case. So let me begin with explaining this formula. So AV, they are the so-called phase point operators, and they span the space of density matrices. And because this is so, by definition, you can represent every density matrix as a linear combination of these phase point operators. And the expansion coefficients then simply form your Wigner function. Okay. And so I said those operators span the space of density matrices. And there's now two possibilities. Either they form an operator basis that is a minimal set of spanning operators, or they are not a minimal set. They are redundant. And what do you choose? And maybe, I think my experience is that people prefer those phase point operators to be a basis for the space of density matrices, no redundancy. But then you run into a couple of problems. So the first thing, has been proved by Zhu, if the set of operators here is an operator basis, then you cannot represent the corresponding Wigner function in such a way that it is Clifford covariant. So remember, we needed Clifford covariance for our simulation result. And if you take this an operator basis, well, you can't have Clifford covariance. Same thing holds for update on the Pauli measurement. If this is an operator basis, you cannot have positivity preserving update on the Pauli measurements. And so then there's a third result that I'm not getting into. So the lesson is base Wigner functions on overcomplete sets of phase point operators. So this introduces redundancy. And if you're willing to pay this price, then you can make everything work. But the price to pay is a more complicated notion of phase space. So in the odd dimensional case, your phase space is just a grid, whereas in the qubit case, multi-qubit case, it now splits into various components. And what separates these components is that you cannot get from one component to one another by translation. So if you translate, which is mediated by conjugation on the Pauli operators, you always stay within one component, can't get into another. It's a more complicated structure. Good, but if you're willing to pay that price, then you get for qubits the same results as you get for qubits in odd dimension. Okay, that was a long story. It is not the result of this talk. So let's move on to the subject of this talk. So I'm ending my review of background and now move on to the real subject of this talk. So I should pause for questions. No questions. Let's just race to the subject of this talk. So there was more to say. I don't have the time to say it. Okay, so now we talk about this hidden variable model that my talk is about. So there is various parts that we want to talk about. So first is our hidden variable model and the result that we have about it. And I believe it is counterintuitive. So let's do a few checks. So we check the compatibility with the PBR theorem. We check the compatibility with Gleason's theorem. And then we go back to interpreting the role of Wigner function negativity. So that's the menu. Let's get started with that. Okay, so maybe one more comment about the older paper, the one with this complicated phase space that I just showed you here. So this is the third in a sequence of papers, and all these papers were such that they revealed something only with hindsight. So we could look at the paper half a year later and ask the question, so what's the really important thing about that paper? And we could answer it only after a certain time. And for that paper, the central result is this. So there is a set of positively represented states, states represented by a probability distribution, and this set is closed under Pauli measurement. That is, if you take a state within that set, apply a Pauli measurement to it, you end in the set. With hindsight, we could see that was really the central thing. And now, the question is, what is the largest such set? I mean, we have constructed one in this older paper, but not necessarily the largest. And we could ask the question, what is the largest such set? Because the largest such set would have the least amount of negativity for its states. Okay, and we have also asked ourselves this question and then came up with such a set that requires no negativity at all. Okay, so here is that definition. So this is the definition of our hidden variable model state space. So if you're ready for it, questions are dying, so I hope you're still with me. But if you're ready for it, here's the definition. So it holds for any number n of qubits. So for any number n of qubits, denote by curly Sn, the set of pure n-qubit stabilizer states. So then the state polytope lambda n is the set of operators with the following three properties. First property, the operators have to be Hermitian. Second property, the trace of these operators has to be 1. So you see this is modeled after quantum mechanical state space. You would have the same conditions in density matrices. Now, third condition, And here we are slightly more relaxed, or somewhat more relaxed than we would be for proper quantum states. The condition is as follows. So if you take the trace of our operator with a projector onto a stabilizer state, projector onto a pure stabilizer state, then the trace of this product has to be greater or equal to 0 for all stabilizer states. So that also holds for all proper density matrices, but for proper density matrices, you would require something stronger. You would require this condition to hold not only for all stabilizer states, but for all states. Okay? And so because we are requiring less here in this definition, our state space has the density matrices included as a strict subset. Okay, I want you to remember that picture for later.
And just to be clear, a stabilizer state is a state that is fixed under all of the Clifford unitaries that you have in mind?
No, sorry, no, that is not the case. The set of stabilizer states is fixed under the action of the Clifford group, but individual stabilizer states are not. A stabilizer state is a state that is fixed on an abelian subgroup of the Pauli group.
But also, can you explain what is the kind of geometry of your polytope, or it's difficult to tell it?
It's too difficult. I cannot explain that to you. If you are maybe a geometer, then that task is for you. I have shown you the 1 qubit picture where it is just a cube. But be reminded.
Yeah, but that's why I wanted to say, right? Because I'm just completely independently looking at something at systems which have many cubes. Because what I realized that people in physics, indeed, like they look at 1 cube, but actually it's not like in geometry and interesting kind of modern objects. It's actually many cubes, and they have to be kind of glued with each other in a very particular way. So that's why I'm asking if you know what exactly is your polytope.
Yeah, I cannot answer this question. I don't know.
Okay,
I mean, it depends on the, I mean, it's getting progressively more complicated as you ramp up the number of qubits. But already for n equals 2, you have 22,000 and odd extremal points. And it's not a hypercube. I mean, it is a very complicated structure. And this is almost all we know. We know a little bit more than that. And maybe I can come to it in 2 hours or so. But it's a complicated structure. That's what I can say. And I want to pose it as a challenge for geometrically minded people.
So you have it like in arXiv, right? In your paper, there are details.
Yes, so you see the preprint number on the title slide and at a bunch of other places. So you can look it up. But I cannot answer your question. You're asking me what is the shape of the polytope? I don't know. Good. But since it is a polytope, so this was a definition. This is our definition of state space. And on the next slide, you'll see a theorem about that state space. But before we get to that, just a general point. So since we're dealing with a polytope, I mean, these are all linear constraints. So we are dealing with a finitely generated polytope. And an alternative description of this polytope is by its extremal vertices. So we have a bunch of extremal points of this polytope, just the corners. And basically their labels are points in our generalized phase space. So this is our generalization of phase space for this model. And the point to make is that this phase space is finite for all numbers n of qubits. Okay. So with this definition, so it's, which was again pretty close to the definition of density matrices, except for that part here, which was more relaxed. We now have the result. In one sentence, the result says everything is positive. So here's the theorem. It has 3 parts. Let's go through them. So for all quantum states in our n-qubit state space, whatever n is, all states can be represented as a probabilistic linear combination of phase point operators, corners of the polytope. So that's positive representation of all states. And the remainder of this theorem is dealing with measurement. Clifford unitaries don't appear here. We get back to them later. But the rest of the theorem is dealing with measurement, namely with the post-measurement state and with the Born rule. And again, so let's look at what we have here. So here we have a phase point operator, corner of the polytope, sandwiched by a projector, by any projector corresponding to a Pauli measurement. And so this is the post-measurement state. And again, the post-measurement state is a probabilistic linear combination of the corners of the polytope. So it's inside the polytope. And again, that's for the post-measurement states. And also, if you're interested in the Born rule, we have a probabilistic representation of the Born rule that invokes the probability distribution characterizing the state before measurement and some conditional probabilities that have to do with the observable that's being measured. So everything is represented positively in this picture, not only the states, but also the Pauli measurements.
Robert,
Yeah.
Peter Shore has a question.
Yes, please. Peter, are you muted?
I'm sorry, I'm muted. I'm sorry, I don't actually have a question. I just had my hand raised when you asked whether we understood. I should lower my hand. Okay,
Okay.
No questions.
Good. Okay. Good. So this is now kind of the central slide of the talk. Yeah? So I defined the state space on the previous slide, and now we are discussing properties of the state space. And the properties are that the states as well as the operations, I emphasize this, not only the states, which would be easy, but the states and the operations are both represented positively. So this is kind of the central result that I want to talk about. So this is a very important slide. It's the most important slide of this presentation. Let's have it on for a little longer. And I think what's coming up next is parts of the proof. Okay, I just want to, yes.
I just have a question about the first item. So
Yeah.
the polytopes that you're working with contain the actual set of all states, but you also have things in there that are not typically considered quantum states, correct? So
That is correct.
Is there an easy way to identify the distinction between the two, sort of like a converse to number one?
The only thing I could think about, I mean, if you want to check a particular point in the polytope, just, I mean, by this formula, you get the density matrices and just look at the spectrum of eigenvalues. But this is really, it's the only answer I can give you. Beyond that, I have no answer. I mean, it is true. The polytope contains density matrices and stuff that is not a density matrix. And the associated simulation algorithm could even treat those unphysical states. Yeah, so it gives us efficient simulation for something that doesn't occur in nature, as far as we know.
Thank you.
I also have a quick question.
Yes, please.
So if I was not interested in Clifford and Pauli measurements, in principle, I could look at the states rather than stabilizers and look for some other states that basically preserve my operations, in the sense that, let's say, rather than Clifford, I'm interested in operations that I can represent efficiently, for example, some other set of operations, and then look at another representation for rho, right? So there's nothing special about Clifford, Pauli, or the stabilizer states here.
I don't know. I mean, try. I mean, I totally understand. I mean, especially if you're working within this framework of resource theories.
Exactly. Yeah.
You could think of modifications of the typical scheme of quantum computation with magic states. So you could swap out the Clifford gates and introduce, I don't know, I mean, match gates, for example. That would be a possibility, and the match gates would come with their own magic states and so on and so forth. Yeah, you could change the scenario in this way. This would be well motivated, but then I mean, you would have to see for yourself whether these statements carry over. I mean, you would have to come up with a according suitable definition of your state space, and then see if you can, for your setting, prove a theorem 1, the counterpart of theorem 1.
I guess one challenging point is how many bits. I guess the same type of questions that were asked before. How many bits? How far you have to enlarge your state? So maybe this is a good choice because your representation is compact or something.
Okay, so let me stick my head out. I mean, one thing, even though we don't know the absolute number, but again, that's really for geometrically minded people, find out the size of the state space. This is a challenge for you. Whoever wants to take it, I would love to know the answer. I believe that the scaling of this size of this set is bad. It's really, really bad. It grows really, really fast with n, probably exponential. I mean, probably worse than exponential. But I mean, for your question, how many bits you need to keep? Really, the question is, how does the logarithm of the size of that set scale with n? And if that set scales polynomially, then the logarithm scales polynomially, then it's probably fine. And if it doesn't scale polynomial, then you would consider it not to be fine. I think it does not scale polynomially, but that needs to be seen. Logarithm does not scale polynomially, but it needs to be seen. However, it is probably, the following is probably true. So I'm sticking my head out here a little bit. We have not written it up, but if we find the time, we will. What is probably true is the following. So you can think of a fixed magic state. So far we haven't specialized what the magic state is. You can fix it to anything you want, and you just fix it to something standard, say the tensor product of T states, fixed magic state. And then you can ask yourself the question, under the update, can you really reach all of the phase point operators on all of the possible updates? Or if you fix your magic state, maybe you stay within a certain region of phase space. And I think that is the case. I would believe this to be the case. And that region, that smaller region that you reach of phase space, if you start with a fixed magic state, that could be comparatively small.
I see.
Could be comparatively small, but that is as much as I'm prepared to say at this moment.
I see. Thanks.
Good. Okay, so now everybody had hopefully time to absorb this this theorem, and so I see that my hour is up. So, Chair, how much time do I have to finish?
Well, take a few minutes.
Okay. Thank you. So, okay, so we want to talk about the update under Pauli measurement. So we have a phase point operator here, one of these extremal points in the state polytope, and we sandwich it with a Pauli projector. And the outcome is a positive linear combination of phase point operators. So we are landing inside the polytope. I want to prove that to you. And the proof, again, is incredibly simple. And to do the proof, recall the property. The third property in our definition of state space was as follows. So if you take a phase point operator, it holds for all points in the phase space, the state space, so it holds in particular for the extremal points. If you take such a thing, sandwich or multiply it with a projector onto a stabilizer state, and then take the trace, you had to be non-negative. And what we want to show is that this property is inherited under Pauli measurement. Okay, so the object we're looking at is now something of the same structure, but instead of the phase point itself, what we have here is the sandwich thing, the phase point operator after projection with a Pauli projector. Okay. So what can we find out about this thing? So every step is extremely simple. So first step is just, I'm using the cyclicity of trace, I'm taking over the projector to the other side. So the next step is super pedantic. I'm just putting brackets So operator multiplication is associative, so I can put brackets as I like. And now I observe that if I have a stabilizer state and a Pauli projector acting on it, modulo normalization, I just get another stabilizer state. Okay, so here's a normalization factor, larger or equal to 0, and here is the new expression. And now I realize this thing I know something about. By assumption, it is larger or equal to 0. And so the whole thing is larger or equal to 0. And so I find that this property up here of my state space is inherited under Pauli measurement. Okay, good. Just that much about the proof of this theorem. And the third part is similar, so I'm not going through it.
So
Good.
do you also have such a theorem for the Luder's projection postulate?
Luder's rule doesn't come up here. I have the Born rule. The Born rule is the third part of the statement.
And then what if you forget the result of the classical measurement?
That would just be tracing over.
Okay, so
yeah,
no,
so that would be just combination of probabilities, and that stays a probability.
Okay, thank you.
Dear, okay, application to quantum computation with magic states. So remember that scheme? So what the theorem has covered, the theorem I showed you on the previous slide, deals with magic states. They are positively represented, and Pauli measurements are positively represented. But the computational setting has the Clifford gates in addition. So we need to talk about Clifford gates briefly. And I'm not going through this in the interest of time, but again, positivity is preserved under unitary update by Clifford unitaries, and the proof is the same, basically what we had. It's just a little bit of cyclicity of trace and stuff. Okay, and yeah, so the consequence is that this also holds for phase point operators. If they are unitarily updated, they land in the state polytope. In fact, we have Clifford covariance. The unitary update of a phase point operator is just another phase point operator, but that's harder to prove, and I don't need that statement. And so, in summary, what we have, and this is the second result here, that what we have is that quantum computation by Clifford unitaries and Pauli measurements on magic states can be described by an iterated sampling from probability functions. So everything is described by a probabilistic update. Okay? And so this is kind of our result applied to universal quantum computation. So the point is that this model is a universal model of quantum computation. And again, both the states and the operators are positively represented. Okay, so that is really the statement, the second main statement of our paper. Disclaimer, we do not claim to efficiently simulate universal quantum computation. Okay, so there can be trickiness in those sampling processes because our state space is now much larger. And sometimes we know this from other work that some, especially if you remember boson sampling. So sampling can be tricky. Sampling isn't always easy just because it's classical. Good. So yeah, I think I need to come to an end. So I said we have consistency conditions to check. Maybe I'm leaving out PBR theorem just for later reference. Our result does not contradict the PBR theorem. So the PBR theorem makes an assumption that is not satisfied in our case. And this assumption is the following, also the point is the following. In our setting, if you take a phase point operator and the tensor product with another phase point operator on a separate set of qubits, this tensor product is not a phase point operator on the larger space. And so this property violates an assumption in the PBR theorem. So we're not in contradiction with this. Gleason's theorem is interesting, and I want to mention that. So, so what does Gleason's theorem say? So in Hilbert spaces of dimension 3 or greater, the only way to consistently assign probabilities to subspaces is in the following way. So it's in the way the bone rule does it. So the probability for that subspace is the trace, is the trace of the projector onto that subspace times some density matrix. That's so Gleason's theorem. This is the only way for dimension 3 and up how you can consistently assign probabilities in Hilbert space. So we do not contradict this equation, but rather we reproduce it. So theorem 1 reproduces it, but an informal version of Gleason's theorem is as follows. So density operators are for quantum mechanics, probabilities are for classical statistical mechanics. And we object to this kind of simplifications of Gleason's theorem because we describe all quantum states by a probability function. And the reason that this is possible is because we are restricting the measurements to Pauli measurements. However, this restriction does not affect computational universality. Good.
Yeah, I have a quick question. Excuse me. Yeah.
Yes.
So you are assigning probability masses beyond density matrices, right? Your whole polytope,
yes.
You do assign.
Bigger. Correct.
Now, then how is that consistent with the Gleason's theorem?
This is not considered in the Gleason. I mean, Gleason's theorem talks about proper. It talks about probabilities assigned to a subspace of Hilbert space. So it talks about what you can have with proper quantum mechanical states. And we are not in contradiction. We are reproducing that. So, I mean, our model talks about more, but in particular, it also talks about quantum states. And the prediction that our model makes for quantum states agree with Gleason's theorem.
So you are making a more powerful statement than Gleason's theorem. So you can get a quantum state even if you assign probability masses outside.
Yes.
So that's pretty interesting.
Okay, I mean, I don't know if it's more powerful. I don't know what the physical significance of the hidden variable model states is beyond the states of density matrices.
But your system is finite dimensional, correct?
Yes. So our probability distributions are all finite. So there is Beltrametti-Bugajski. This is how we differ. This is one way in which we differ from Beltrametti-Bugajski. That our model is finite.
Okay, so yeah.
Okay.
So it might be more difficult, but okay, something to look into. Okay, thank you.
Good. Okay, so I really raced to the end. I think I talked enough about negativity. So our point here is no negativity required, neither in the states nor the operations. I have reached my conclusion. So we have described the hidden variable model for universal quantum computation, where all states, operations, that is Clifford unitaries, and measurements are represented by classical probabilities. No negativity is required anywhere. Disclaimer, we do not claim the efficiency of our simulation algorithm. There is an outlook, and I run out of time. Let me just say, the interesting questions are those, in my mind, are the geometric questions that were already thrown at me. What is the shape of that state polytope? How can we characterize its vertices? Can we classify them? Can we know their number? Where is quantumness hiding in these extremal vertices? So we know a little bit about it, quite a bit about it, but we know very far from all. So thank you very much for your attention.
Thank you very much, Robert, for an interesting talk. That raised a lot of discussion. And unfortunately, my computer crashed your talk, but I'm back. And Jarek Duda has a question about whether you can simulate Grover or Shor algorithms this way.
Well, in principle, yes, but in detail, you would actually have to do a lot to make it work. I mean, you would have to know. I mean, there's this update of the phase point operators under Pauli measurement and Clifford unitaries, and all of this had to be worked out in detail. And there would be quite a lot of work. But yeah, so you basically So let's go back to the theorem. Where is it? Quite a bit back. Okay, so you see that in this theorem, there appear lots of probabilities. So we have just proven that these probability distributions all exist. But if you want to do an actual simulation, you actually have to know what they are. And for that, you have to work quite a bit harder.
So John has a question. John, you must.
Hi, yeah, sorry, just difficulties unmuting here. Yeah, in the proof of the preservation of the probabilities, you introduced these Q probabilities. And I was just wondering, maybe I'm missing something obvious here, but shouldn't they form some sort of Markov transition mechanism?
Markov, yes. Yes, I think so. I mean, I do not exactly know what a Markov transition mechanism is, so I'm thinking of it as kind of no tails, no memory tails, yeah? Kind of probabilistic update from one time step to the next, and that's exactly what you have here. So if you if you look at this expansion here, so these probabilities. All that they depend on is the state in the previous step and the observable that you're measuring and the outcome that you're getting. So this update only depends on the last moment in time, just before a measurement. Am I answering in the right direction?
Yeah, that's intuitively what seems to be going on, but I just thought it might be nice way to formulate it.
Yeah.
Again, if you were doing successive measurements, the endpoint probabilities really should be described by this transition mechanism, just done iteratively. Yes. So you're just hopping around space with a transition mechanism.
Exactly. Yeah. And so it's really, maybe another way to phrase it, it's kind of a diffusion problem. You're hopping on a graph.
Yeah. It's sort of like, I hate to say this, maybe a discrete version of Nelson's stochastic mechanics, if people are aware of this, where he tries to define or tries to describe the Schrödinger theory in terms of a diffusion process. Again, there are restrictions on that, but yeah.
Okay.
Anyway, maybe thanks for the talk. Yeah.
So this reference, this Nelson thing. Maybe you could, I would be interested in the reference. So if you could send that to me, I mean, you find
sure.
That'd be very nice.
Nelson. John, what is your last name?
Goff.
Are there other questions?
Hello, can I ask a question?
Sure.
Hi, Robert. I see. Thanks for a great talk. I just had a question about you on your slides about Gleason's theorem.
Mm-hmm.
So if you could go back to that. So you were trying to. You were sort of objecting to this informal version of Gleason's theorem. So one question I have perhaps maybe is the following. So in the, I think one thing that you have in the case of probabilities for classical mechanics or even of density operators for quantum mechanics is that you have some way of composing systems together. So tensor products or the products, product states. And does that work for this kind of probability description that you're giving, or?
Yeah. So this is.
Yes, I think that's
Thank you very much for your question. So, okay, I was a little bit brief. So this is exactly the PBR discussion. So, and this is a property that our probability distributions do not have.
Right.
So another way, as it is written here, so if you have the probability function for tensor product of states, again, from some perspective, although I don't know why that would be required, but from some perspective, the probability on the tensor product of states you would want to be equal to the probability function on the first state times the probability function on the second state.
Mm-hmm.
And this factorization probability we do not have. Okay, we do not have this thing. So yeah, our theory simply doesn't have it. But we know one thing. So we know, so there's a result here that I not into it, but decided not to mention it. So this is the result from Angela Karanjai. So basically, what this result says is that if you want to describe contextual phenomena on n-qubit systems, the factorization property that I just mentioned, you cannot have.
Mm-hmm.
So I would flip, I would flip the question around, and I would ask you, why do you want it?
Well, I think it is. I think if you had it, then you would have a classical simulation of universal quantum computation, right? So I think that's one way in which you can say why.
Yeah.
I mean, in a sense, like as you were saying, like the first time you stated this result, it kind of seemed counterintuitive.
It still does.
And I think one of the yeah, I don't know. I think if you had this property, then you could build an efficient simulation. I think, right?
Possibly. I would need to check. Yeah,
right.
but
So, I mean, my point being, if you want to simulate a large circuit, then you could do it. You could treat subsets of qubits independently somehow, which if you don't have this product property, you can't do, I think.
Yeah, but I mean, you have
sort of state space is growing, as you mentioned several times.
Good. Yeah. So just for the benefit of everybody, we do not have this factorization property. That's a critical property of our model.
Does Dan Brown have a question?
Hi, Robert.
Hi, Dan.
Thanks for your talk. I have a quick question about these extremal operators. So you called them phase point operators.
Yes.
Are they always associated with phase point operators that define a Wigner function, or are they disconnected entirely from Wigner functions? What's the connection?
What is the connection? Thank you for this question. Well, I mean, as yeah. Let me go back here to this slide. So, okay, so this was in the first part of my talk where I was just reviewing, and this was the final qubit result with the negativity that we've got. We realized, or we suggested that your usual grid type phase space splinters into these many components. And then we have a Wigner function on that state space, which is this thing. But I mean, the question is now, is this still a Wigner function for you? I mean, it has all the nice properties that you need: positivity preservation on the Pauli measurement, covariance on the Clifford unitaries. The question is whether you call it the Wigner function still. So if you call it the Wigner function still, then there is a connection. So Dan, is this still okay for a Wigner function?
Yes, I'm happy for you to call that a Wigner function.
Okay, so then let me move on with my answer. This was on the Outlook slide, but I didn't have the opportunity to get into this. So let me say it now. So we can prove that if you look at these old phase point operators, I mean, the early 2000 phase point operators from this PRA for the qubit, multi-qubit scenario, they are also extremal vertices of our state polytope lambda n. So this is not obvious why this should be so, but it is the case. And so on a technical level, there is this continuity. There is continuity. So we can use the old phase point operators, and they remain phase point operators for extremal vertices in our much larger polytope. But just the thing is that now these phase point operators, they are not alone. There's many, many more, some of which we do not know the structure of.
Thank you.
So thank you, Robert, very much. I think we should wrap up now because we've been going almost an hour and a half. And it was a really nice talk. And we look forward to hearing more about it as you develop this theory. And also, we look forward to everybody coming back next week. Bye-bye. Bye-bye.
Bye, thank you. Geometrists, get involved. Geometrically minded people, please get involved. Thank you.
Thanks. Bye.
Thanks.
Bye.
Bye.